Thank you for inviting me to do this. We have only 37 slides, but having given this talk last night, I realized it's quite easy to talk a lot longer than a 60-minute slot would like to have it happen. There are many slides I'm going to show for graphic purposes with detail on them that I won't be discussing except very cursorily, but they all are covered in case studies that are referenced with links at the end of this presentation. Okay, so context for all of this. In the 90s, basically we had a major project that was funded by the Office of the Secretary of Defense and then eventually DARPA that attempted to understand what was going to happen after lean. And what that resulted in after a lot of workshops occurred was an attempt to understand what really makes systems agile. And I'm not talking about software agility as you may have heard of it. I'm talking about what really gives the ability for a system to deal in an unpredictable, squirrely environment. And what we did was we analyzed hundreds of systems by invitation from people who said, we think we have something that has those characteristics, come and look at it. And we did that process over a number of years in an attempt to find out what's a core set of fundamentals that they all exhibit. And we accomplished that in the 90s. There's been plenty of it written on it. We won't talk about those tonight other than to use that as a background to say now we're doing this same process again, except instead of trying to understand what makes systems agile, we're trying to understand what makes system engineering processes agile. And we're not trying to invent something. We're trying to go analyze what are people doing that's actually working and what makes it work. And that means we aren't really interested in some of the practices that they're using. What we're more interested in is what's underneath those practices that really makes them critical to providing agile capabilities. I keep trying to use my keyboard forward. That doesn't work. Okay, so the agenda is I'll give a quick overview of what systems agility really is all about. Then we're going to quickly go through 4 different case studies that came about from 3-day structured analysis workshops with a traveling group of some 20 people that sat in at the invitation of 4 different hosts. You can see them up there. SSTPAC is basically SPAWAR, System Center Pacific. We'll talk more about that later. I'll go through those 4 cases with the intention of using them as foundations for leading to what I then call the overview of the project findings. And the project isn't done yet, so the findings in some sense I have to say are preliminary. But we feel pretty good about them so far. We expect to do some more vetting of them, and there may be some minor changes to them. We'll do a little epilogue, assuming we have the time, that will focus more on the hardware development infrastructures for agile hardware development. Okay, so why does agility matter? I expect all of you have some understandings of why it does matter, and it's basically because the environment that our system engineering processes and that our system engineered products have to go operate in are unpredictable, uncertain, risky, variable, evolving, and that pretty much covers almost every kind of project that we work on in today's environment. And so this is a heuristic framework of 5 concepts that basically we have asked our hosts in those 4 locations to tell us what is capricious about your environment and what is uncertain about your environment that made you go to an agile process. And we'll look at some of those basically in the words that they provided as opposed to the words that we might have after the fact said there were many things you didn't put down there that were clearly also important. Okay, so how does some of that translate into a system engineering process? The curve environment of a process, and this is a pro forma. It's got 2 bullets each. You could put lots more bullets down there, but it's to give an idea about what it looks like when you start to try and understand the environment that you're going to work in. And again, I'm not going to read a lot of these slides to you because I figure you can read it while I'm talking. But you can see up under the unpredictable one, urgent need occurs. Well, we've seen that in almost all of the defense contractor host environments that we've worked with, where they're working on a contract and all of a sudden their customer says, forget what you're doing, I need this other thing done, much more importantly, right away, stop that, start this. And there's no prediction on when such events will happen, but they do happen, as we saw in the places that we talk to quite often. Okay, so agility is something that basically is employed to sustain an operation, to sustain a product that gets put into the field. And in order to sustain the operating capability of the process or of the product, you've got to have a proactive awareness of the situations that you need to respond to. And we're going to talk quite a bit more about that because it's become one of the most important findings that we've come to understand. It doesn't matter how agile you think you are, if you don't have up-to-date awareness and alertness about the need to employ that agility, why bother having it? And so we're really seeing that the people who do their agile system engineering environments well have a dedicated team of people who are doing nothing but observing what's going on in the outside world that's going to affect what you're doing here. There are 5 processes, there are 5 responsibilities, I should say, that all agile processes must have in order to be effectively agile. And we're not going to talk about these in detail, but basically we're looking at an agile process or an agile product as consisting of a resource pool of modules that can be dragged and dropped into response activities, and they can be dragged and dropped into an immediate need response capability effectively because there's an infrastructure of standard interfaces and rules about how these things can interface with each other right away. So in order to make all this work in a sustaining way, you have to have 5 responsibilities covered either by people, by groups of people, or by processes. But to the extent that they aren't absolutely manned or processed at all times, you've lost a good deal of your potential agility. Okay, so somebody has to make sure that the mix of resources evolves as needs evolve for new kinds of resources. More importantly, in some sense, you have to make sure that those resources that you claim are available are in fact ready for use and not sitting there in an inventory because somebody returned it from its last usage and it's all rusty, or it's untrained if it's a person. So somebody deals with resource readiness. Very importantly, as I mentioned before, is situational awareness. Who or what process is responsible for monitoring, evaluating, and anticipating the operational changes that are going to happen. Then, of course, there's somebody who, upon need, has to grab the appropriate resources and assemble them into an effective response. Those resources are often mainly in system engineering processes. They are people, but they are also other things that we will see in some of the examples that we look at. And finally, the 5th responsibility is somebody has to take responsibility for evolving that infrastructure as time requires with new things that aren't effectively available in the current infrastructure without some change. But the infrastructure evolves slowly, whereas the resources evolve a lot more rapidly. Okay, so here's the iconic graphic. An Agile system is basically a response construction kit. And we all, I expect, we all have some understanding of what an erector set is and how it works. You've got a series of components that you can assemble into a variety of different things. And you can do that because there are a set of rules down there on the bottom, sockets, signals, security, safety, service, that dictate how those interfaces can work together. So this is basically, I call it the iconic diagram. But to put that diagram in the context of a process, I think most of us also have a fairly good understanding for how American football works. And you'll notice it's the same architecture, except now we've got different kinds of players as resources. We've got game plans. We've got plays that can be invoked within game plans. And we have a variety of different things at any one given point in time on that field that these resources are brought together and assembled into a response kit, if you will. Okay, so the earlier work that started in the 90s basically came up with what I just showed you as a common architecture that is present everywhere we see an effective Agile process or Agile system. To take the architecture one step further, we also discovered a set of 10 design principles that flesh out that architecture into something meaningful for a given domain of application. I'm not going to deal with these because they've been dealt with extensively elsewhere. I've referenced an INCOSE webinar that specifically deals with what these are, but you just by reading them quickly, you can get some feeling for what those are all about. But they are, that architecture I showed you and these principles are basically structural concepts that enable agility. What we really want to talk about today is the behavioral concepts that express themselves as agility in action. We also make a distinction between System 1, System 2, System 3. And we found we have to do that very clearly when we go to these analytical workshops because people begin to talk to us about a system and a system characteristic, and it gets very confusing if we don't know which system they're talking about. System 1 is the system, the target system. It's a system that's being built. System 2 is the process system that builds System 1. System 3 is the learning and innovation system that constructs and modifies System 2. And all three of those different systems are really present in most of the conversations we all have at one time or another, and often the distinction isn't made and it gets confusing. Some of the things we're going to look at today in the 4 different examples, 3 of them are going to be about System 2, the system engineering process. One of them is going to be about System 3. Basically, it was at Lockheed in Fort Worth, and it was the transformation process of tailoring a safe approach into something applicable for what was going on at Lockheed Fort Worth. And so we'll look in one instance at a System 3 concept, and at 3 other instances we'll look at System 2 concepts. One thing that's very important to understand, and it was really underscored heavily in all the workshops we've done, is having an Agile process is absolutely of no value if it is not building an Agile product. And the principal reason why that is true is because the essence of an Agile process is constant learning and remodification and evolution of the work that's in process, which often means what we just did recently, we now understand isn't correct. So now what we have to do next is fix what we did incorrectly last time and forge ahead. Well, if the target system you're building doesn't accommodate rapid change in itself being an Agile system, it doesn't matter how Agile you think your process is, it can't operate in an effective manner, and we'll see some examples of that. Software people don't talk about this because they have an invisible to them, the water they swim in to them, environment with object-oriented development platforms and with, in the case of web development activity, loosely coupled web pages, so they don't even think about the need to have an Agile product. But when you start moving into the hardware environment, it becomes critical. And we'll see some of that. Okay, so here we are at Navy System Center Pacific, SPAWAR System Center Pacific. Now, I'm going to show for each of these the curve environment that the host presented to us. And I'm saying it that way because after the fact, we could have added quite a few things underneath some of these areas that would have been appropriately exposed by the host. In this case, the proformas we sent out to all the hosts had 2 bullets under each of these, and so our first host gave us 2 bullets back. But basically, what's going on at Navy SPAWAR there is they have a variety of customers, all within the Navy, that they're servicing who want off-road autonomous vehicle technology developed. In many cases for different purposes, but what's going on is the group that is doing this basically has come to understand that what one of their customers wants in one of the 6 or 7 technologies that have to be developed can in fact be used by others, and so they end up running a portfolio type environment where everything that they produce goes into a product lineup that could be used in other projects for other sponsors. And all the sponsors buy into this because even though one sponsor ends up paying for something that others are going to use, they in turn get to utilize what the other sponsors have also paid for. And so it's a very synergistic environment there. I'm not going to read through these things. I just want to give you an idea for how they describe their environment in terms of the unpredictable and certain risky and so on activities. Okay, so what we found there at Navy SPAWAR was something that is known as the WAVE process. A lot of work has been done in the literature on the WAVE process, principally led by Judith Tallman out of MITRE, and it was all paperwork for quite a few years. This, to my knowledge, is the first and the only mature application of the WAVE process in a very serious way, knowably called the WAVE process. And I'm going to say it that way because as we looked at other analytical environments that we studied, we found that there are variations of WAVE going on in many places with no recognition that, in fact, what they're doing is WAVE. But the key thing about the WAVE process, up there at the top, you see 2 development cycles back to back. They are identical in terms of what happens, but they are back to back. When you finish one development cycle, you begin right away on the other one. And what you do is you hand off the waterfall processes that generally have to happen next, like integration, test, validation, and verification. And that's why it's basically called a WAVE, because you keep working as developers on successive development environments, but there's a staggered activity that follows up each development increment with the necessary integration, validation, and test. And you'll notice that the process is, I'm going to tell you at the moment that the process is highly agile, but at the same time you'll see PDRs and SDRs and the kinds of things that government contracts require of you. And what we found in virtually all the cases, because the 4 that we've looked at are all defense contractors, is they've got a relationship with their customers that recognizes the value of having something much more agile than what they've had in the past, and so they found ways to get what they need in terms of gated progress without impeding the ability of the agility. And we'll see some examples in more detail of that. This is just a quick reference to show that the kind of resources that are employed at Navy SPAWAR can be assembled into a variety of different activities, whether it's integrating onto different vehicles or whether it's solving problems with IPT groups or doing the validation testing. A lot of these resources are shared across a variety of different activities. And all of this is explained in some quite detail in the case study paper that is referenced up there in the left-hand top corner, but also on the final slide for what we're going to look at here. Okay, so some of the notable concepts there. I mean, they were doing 6-month delivery increments, and they have a product line approach. They don't use that word. They never said they had a product line approach, but as we'll see, especially when we look at Rockwell Collins on the nature of a product line, in essence means that you've got a series of components in a library that the next project you have to work on doesn't have to develop from scratch, because it's got maybe some 30 to 60 to 70% of those components already done that could be used in a variety of different applications. One thing notable with the Navy, especially since they're a government organization, is all of their development was done by subcontractors on the outside, but the Navy took responsibility for the architecture that allows all of these things to work together in a portfolio environment, which is like an OSA, an open system architecture. And they took responsibility for integration, test, verification. That's something that most people in the government say the government shouldn't get involved in that. Well, this group did, and it showed big savings in cost as well as in time by taking that responsibility. Okay, now we move on to Northrop Grumman. Northrop Grumman is basically a pure software environment that we looked at. Scrum-based at heart, though I want to call it Scrum-like because they did a lot of modification on it. But in essence, what they're doing is building a system of systems web hub, in that they have 12 different customer groups from all of the different military services who are basically wanting to ask questions about logistics. Where's my stuff? And variations on those kinds of logistic questions. And the answer lies in one of 22 independent databases. And Northrop Grumman basically provided a centralized hub where you could learn one set of way to ask questions, and that hub would then figure out how to translate that into the kinds of answers that could be obtained from one of these 22 independent databases. Very key, 22 independent databases. Those databases change at whim, without any warning, whenever they want to, and Northrop Grumman has to swing into action and fix up those interfaces for the changes that one of those databases put. They also have another set of very interesting problems, in that they're doing 6-month development increments, and in those development increments they've got 4 sprints of 4 weeks each, and in those sprints the customer expects a certain set of features to be added for the next release that comes out in 6 months that weren't there before, and everything starts out fine on day 1 of the first sprint until day 2 happens, and all of a sudden 22 high-priority security bulletins come through that must be responded to within 15 days, and there went most of your feature development capability. And so they're in a very volatile environment. The quantity of high-priority security bulletins that come in is unpredictable. It's spiky. It has large swings. On average, it takes a good 30 to 40% of their development's capability for attention, and that varies in every sprint. Okay, the other thing that's very uncertain in their environment is the obsolescence. They use over 1,000 different common off-the-shelf software components that they've got from COTS environments, but also from open system software environments. And those things go end of life. And so they have to deal with the end of life that keeps happening in these things. They've got a very volatile environment, and one that's highly unpredictable in terms of what are we really going to accomplish in this next set of in this next increment of feature development. Okay, so here we see something they're doing that, by golly, looks also like a wave concept. They never used that word. They never recognized that concept. But what they're doing in 6-month development cycles is they do them back to back. For 6 months, they develop what's going to happen for the next release, and then they pass it off to the accreditation team. But the development group doesn't sit there and wait for accreditation to happen. They start right away in on the next set of evolutionary feature development. That accreditation finishes, and then it gets put into operation for 6 months. and eventually you put it into retirement. So you've got a wave process going there with 3 simultaneous releases of interest, and that's important because when the security bulletin comes in, you have to go fix all 3 releases simultaneously. You've got to fix what's released in operation, you've got to fix what's under test accreditation, and you've got to fix what's in development right now to deal with those security bulletin issues. Okay, so here's just another example of the kinds of resources that are key for them that they can manipulate and reconfigure, and the different kinds of things that they have to do. And again, there's a lot of information on this slide, and we could talk for hours about what it is, but you can also read the case study paper, which deals with all that detail. So, some of the notables there. They're using the product line approach without any real recognition in a different way than we normally think of product line. But the core essence of product line approach is that you have a library of componentry that can be used in a variety of different ways on different projects. And in the case of Northrop Grumman, the way that developed, and this came about through lessons learned over time, is they realized that there are 3 different Scrum teams that were working on successive project activities. Whenever they had to do graphical user interfaces, which they refer to as widgets, or the new features that they had to put out there, they would develop them from scratch. And what they learned the hard way is it would be much better if they would develop some standardized concepts that could parameterize a lot of these graphical user interfaces in such a way that you could use the same GUI in multiple requirement activities just by changing some of the parameters that were in there. And so, in essence, they developed a product line approach for a lot of the work they had to do there, too. Very key, they have to look ahead on, another lesson learned, I should say. This concept of 15-day security bulletins that come in is always a shock. I mean, here it comes, and you've got 15 days to make sure it's fixed everywhere, and which is highly disruptive. And so they started a process that basically said, let's try and get a leg up on this and spend some time every sprint looking out there with our security people for what do we see coming down the pipe before the security bulletin hits us. They started doing the same thing with the COTS OSS obsolescence activity. They have 1,000+ of these things. They can't look at them all every sprint or every increment, but they do a rolling look through the variety of things they have to see what's coming end of life, as well as what's likely to have some security problems. And so they get advance warning and the ability to do some coherent scheduling, all because they're very much aware. They've got a proactive awareness activity going on, looking out into the future, trying to get a leg up on what's coming down the pike for them. Okay, we'll move on. Current environment for Rockwell Collins. Rockwell Collins is, I think, not even arguably, it is the world's premier military radio producer. And they've maintained that for a long time. And they're very protective of staying out in front of that whole marketplace with the best and the newest capabilities that need to be done there. And one very important thing on how they do that is something we'll discuss in a slide or two. But for them, they're looking at a customer base that, as they said, keeps asking, they cherry pick. They look around at a variety of different things that are available out there in the world, and they say, we want all of those. And that's real nice, except all of those won't work together, for which the customer has no appreciation and needs a lot of feedback from Rockwell Collins to help them understand that. Okay, so these are the kinds of things they put up as to why they went through an Agile process, which they describe as Scrum-like and safe-like, by the way. But it's very much a version that they've homegrown that deals with software, firmware, and hardware Agile activity. And we'll see that in a bit. Here's how some of that translates into the Agile architecture pattern. But importantly, here's a picture of kind of what they're really doing. the bottom level I call code, because I don't know if firmware people want to think of themselves as programmers, but in fact that's what they're doing. And down there in the firmware and the software environment, there's three varieties of things that get employed. Some of that is common, which is to say they built it before. It's in their product line library, and they can reuse it again in this project that's now happening. And when I say this project, there are multiple projects for multiple customers going on all the time. They try and make sure that they can employ as much as possible from everything they do in a product line concept so they can reuse it later and provide another customer a more rapid delivery and a less expensive delivery, because not so much has to be developed from scratch. But they also have government-supplied code. And basically the government sometimes, when they pay for some of this kinds of work to be done, whether it's with Rockwell Collins or with other people, they take ownership of it, and they will then impose upon some of their contract requirements that you employ this particular piece of firmware or this particular piece of software. So there's common stuff, there's government stuff, and then there's stuff that has to be developed from scratch because we don't have anything around that does that yet. That goes into firmware and software, which goes up into components on electronic boards, where they have to build schematics that are, again, common and developed. So they reuse what's in the product line, but they also don't always find a large part of what this next contract wants. So they end up having to build a lot of electronic cards that then have to get stuffed into a box of some kind, and sometimes that has to be a new box because they don't have one that they can put these new cards into with enough connectors on it. Other times it's an LRU, a line replaceable unit, which is they have something in their product line inventory that can be applied in this activity as well. Okay, so here's an interesting concept, and it's one that we think is a real strong takeaway from the work that we've been doing. Basically, they're at the lowest level. You see they've got software development happening in a very fairly standard Scrum, iterative, incremental, constant cadence development approach on feature epics. Then you've also got firmware, which happens on a little bit different cadence, but not too differently. But it doesn't necessarily finish their increment at the same time that the software people finish their increment. So maybe you can't test. You don't want to hold up the continued software development until the firmware people get their stuff done. You've got the same thing going on at the hardware level, where you've got incremental iterative development of circuitry and cards that can be plugged into chassis, also on a different time frame basis, because you can't do you can't do most of the hardware in an Agile environment on the same kind of 2 to 4 week cadence that you can do with software. There's a very different set of constraints. So what they've got is incremental iterative development happening in all those different categories. And they have found a very comfortable way of being able to do integrated tests at various points by basically saying, we don't need to wait until the next increment of firmware is ready or the next increment of hardware. We can use the last increment. And so as they go through at the software level, doing their successive integration and test activities, they'll use the most recent completed increment from the others, and they don't necessarily need for it all to happen on a synchronized basis. So that's what we call it at the top, asynchronous, mixed discipline increment alignment. Okay, some notables. Product line architecture and strategy is the enabling concept there, and one of the lessons that we learned as an analytical group going through 4 different operations is we saw all the product line architecture concepts almost everywhere. Actually, I should say we saw it everywhere, it was only recognized in that phrase, product line, by Rockwell Collins. But in fact, we saw component libraries developed at maybe SPAWAR. We see it happening at Lockheed. We saw it happening at Northrup Grumman. Without specific recognition on the parts of those hosts that they were in fact following a product line architecture concept. What else is worth talking about here? Very key for them. In order for them to stay ahead is to do something called the market requirement document. And what they have, did I have that on my diagram? Let's see. No, I actually don't show it on there. Okay, market requirements document is a group of people who are constantly looking out into the future for what kind of technologies are emerging that we need to have capability to employ with designers and engineers who understand it, what kind of needs are our customers and our potential customers going to demand of us in the next 6 months or 12 months. They've got a future-looking group that constantly iterates through this market requirements document. And as they do that, they basically it's a secret document inside. They share it with almost nobody except the system architects and, of course, with the chief engineering group, so to get the chief engineering group to agree that, yes, we can do those things. And then they're parked in the market requirements document until such time as a project comes through that they say, hey, you know, here's something that we want to have in our product line down the road, and here's a project that could actually help make that come to pass. Let's move this out of the market requirements document into the project requirements. Other times where they see things they need, but they don't see a project that they can squeeze it into, they'll fund it internally and with our R&D work. But the key point there, I think, is that they've got this group whose sole function is to sit there and look to the future and constantly figure out how do we evolve this product line that we have, how do we set things up so that we know when we can take advantage, when do we have an opportunity to actually pull something like this out of the future and make it into the current. Okay, then Lockheed, Fort Worth, no less. Again, this is the current environment that they presented to us with some understanding of what we were looking for and some understanding of the situations they were faced with that made them decide they had to go to an Agile approach instead of the previous waterfall approach. You know, in the case study, what we talk about principally is urgent operational needs. And they're doing F-22 and F-16 weapon systems upgrade. And at first, when we went out there, some of our people said, well, this isn't system engineering, this is maintenance of aircraft. And we saw that same concept at Northrop Grumman. And one of the things that we've come away with is a strong understanding is Agile systems don't get developed at one point and then just go into a maintenance phase. They constantly evolve, preferably with a strong system engineering attention all the way through its entire life cycle. And that's what we saw going on at Lockheed. Yes, they have incremental deliveries for specific feature sets that one or multiple customers want in the next contract that comes through. But they also get installed into an aircraft that keeps coming back. And so they see the same aircraft over and over again. And they basically came to understand that the concept of open system architecture had a lot of values in addition to being strongly suggested by the customer, and I should say plural, the customers. They also realized that with an open system architecture in the aircraft and the concept of a product line library of components they produced previously that they can now use again because they've got a common infrastructure, open system architecture, I should say, that allows them to reemploy things done previously on things now being needed again for a different need. And that especially helps them deal with urgent operational needs, where the customer says, forget what you're doing for me that we decided upon most recently, because now I need something else done quickly instead. And you see the other kinds of things that have to be dealt with there. And basically, in all cases, the curve environment is what justified and even drove each one of these host sites to move away from what they had been doing before, which was various forms of waterfall, into some form of agile, I should say agile system engineering. And in virtually all cases except Northrup Grumman, all of them were dealing with hardware as well as software. In the case of Lockheed, the internal Lockheed group deals with software development, and they have outside contractors that deal with the hardware parts. Okay, a couple interesting things. Let me see what the next slide's going to say. Okay, a couple of interesting things that were going on at Lockheed. And again, at Lockheed, what we did in the case study was to focus the case study on the transition process of going from a waterfall environment to an agile environment, which was inspired by SAFe, the Scale Agile framework, but in fact in need of great tailoring in order to fit the environment at Lockheed. And in fact, it would need great tailoring to fit any defense environment, because the standard SAFe approach currently is oriented toward the kind of incremental development that works very effectively in a software-only environment, and it doesn't recognize accreditation periods of time. It doesn't recognize long increments that often have to happen in order to get the kind of DoD features that need to be developed. Something very important there that we recognized, I have here on the second activity over, called process instrumentation. And it's another key thing that came out from many of the places we looked, where it's part of the awareness of what's going on. In this case, it was internal awareness, and the work was based on a lot of Reinertson's flow concepts, and deals with the ability for queuing theory to help you understand what's going to happen in the future to your cycle times based on what's going on today on the size of the queues you have. And the queues of importance to Lockheed were at least in two areas strongly. One was in test facilities. You've got a lot of projects going on at the same time, and there's contention and competition for the time needed in the test facility. And so you start building up a queue of people waiting to get in the test facility. You also have queues building up in terms of user stories that are being fed into a Scrum team over some series of iterations and increments. And the size of the queue of things to be worked on also, I mean, basically what the concept is, you can look at these queue sizes, whether it's for a facility like a test lab, or whether it's the feature sets being ready to work on by a Scrum team. You can look at the size of those queues, and you can predict what's going to happen in the cycle time. And in a very simple sense, as there are more complex senses, a simple server. In one case, the server is the Scrum team, or in another case, it's the facility for testing. A simple server loaded beyond 85% is due for chaos. And it basically says it happens because things happen that you can't predict. And so if you know how many hours your Scrum team has to devote to development work, and you try and use 100% of that, you're in big trouble, because if anything unpredictable happens to them, they'll never catch up to the schedule it has to have. So the concept of measuring your queue sizes in various kinds of bottleneck facilities is extremely valuable in predicting what's going to happen down the road for your cycle time. And since it's predicting. And since you can do this in advance of the trouble, it gives you the ability to make some changes to head off the trouble situation that's coming. Okay, interesting. Lockheed was basically a waterfall environment, and today they're a safe-like environment. And it took about 2.5 years to actually go through the full transition process. And it's not to say it took 2.5 years before anything good happened. Good stuff happened all the way along. But about at the end of 2.5 years, the transition team that really managed the cultural change, the training changes, the process acculturation activity that had to go on, basically got to a point in 2.5 years of saying, okay, our job is done because we've got these concepts embedded so well in the group that's actually doing the work that now it's their responsibility to continue the future evolution of the tailored safe process that we're employing. Okay, 1,200 people trained from the top to the bottom. Executives went through the training. It was 3-day training. I think a day for sure was safe-based. It may have been 2, but then there was a 3rd day that was Lockheed tailoring-based. A lot of people involved in that. Another very interesting concept there, something I refer to as a preliminary SIL. They refer to it as an agile non-target environment. They basically set up an integrated test capability long before they had stuff to test. And what they had in there were simulations of the stuff that was expected to come. But very interesting, they also knew that some of the devices that they had out with their subcontractors and expected delivery on were not really too very different from devices you could buy on the marketplace already. They were just much higher performing or higher fidelity. And so they would stock this environment with low fidelity COTS devices that will eventually get replaced by the higher fidelity units in order to advance the abilities for doing integration and test work out between the various components. So you've got a mixture in there of simulation, you've got a mixture in there of finished devices, and you've got a mixture of low fidelity stub holders for the moment devices. Okay, I'm going to move. Open system architecture. I mean, they basically, I think I already covered that. They basically came to understand along the way that there was real value in having an open system architecture in the aircraft environment, so that in fact they could reuse componentry as well as satisfy the customer who's pushing this concept very, very hard. Okay, so something very important that we learned through all of this. We started out believing that instead of a waterfall process, that we're going to see something that looks like what you see here, which is to say 7 life cycle stages that all can be happening simultaneously and asynchronously whenever engagement criteria says, okay, it's time to do some more of that concept work or some more of that production work or time to retire some of this stuff. Very importantly, we've added the seventh stage we call research. I don't like that word because it sounds cobwebby, but it's recognition that the rest of that Agile circle of the 6 standard IEEE processes really are of no value if you don't have very good alert awareness about when you need to employ that Agile capability. And we saw it in every place we looked in one form or another that their success was really driven by their ability to understand what was going on now inside with internal instrumentation, what was going on in the outside world that was going to require something different than what we've been doing. This circle diagram, by the way, is completely consistent with the words in the ISO standards. Most people think that the ISO standard prescribes a sequential waterfall approach. It does not. It was basically the Defense Department and their need for gated approvals that passed that overlay under the IEEE standard. And so this is completely consistent with the words in the current standard, other than that we've added the research stage as a very critical one. Okay, emerging fundamental principles. Project situational sensing and response. Team members engagement, sensing and response. We saw that strongly, where there was a very proactive monitoring of are people engaged or are they just punching a time clock? And what do we do when we find the time clock puncher and the person is just going through the motions instead of the person who's really engaged in the mission? Development issues, sensing and response. Issues that come up in the development environment. It's very important that you're quick to sense those issues and to be able to respond rapidly. Okay, sense, response, sense, response, sense, response. You see this in a variety of areas there, followed by evolution, evolution, evolution. So there's three basic concepts fundamentally that we see that are necessary in all the things that we looked at in order to make them successful. Sense/monitor is awareness. It's the driver of agility. Ability to respond and mitigate. It's the action that expresses agility. And evolve is applying the learning is the sustainer of agility. Okay, so that basically gives us a framework of three categories of fundamental principles that don't look at all like what you read in the software manifesto, but in fact the software manifesto isn't, or I should say, Scrum and safe or of absolutely no value if underpinning the kinds of things that they have up front in your face about what makes them work. This is what makes them work that underpins it. And one of the questions you ask is, a lot of people said to us, and they said, well, one of your fundamental principles got to be iterative incremental development. And I said, why? What's fundamental about that? And we walked into this whole thing saying we aren't going in believing that anything is necessary until we see that it's necessary. And what we've come to understand about incremental iterative development is it has a purpose. Its purpose is the bottom part in the evolutionary concept where you're trying to learn before it's too late what you should have done, what you need to do. And in the software environment, short sprints are very effective at helping you learn that you didn't quite do what should have been done the last increment, but you can fix that in the next increment or in the next iteration. So there's a purpose for iterative incremental activities that can in fact be achieved other ways as well. Now in software, the easiest way is incremental iteration, but if you're trying to learn with time pressures, I've seen operations where basically you've got 5 competing activities going on at the same time, and you got to pick the one that won because you need something, in a very short period of time, and you can't incrementally improve anything. You've got to come up with a good solution. So there are other ways to accomplish the need to learn and select good things. Okay, in summary, I'm not going to read through all these. The generic findings we have that are key, the top one, I went through that. That's those 3 categories of fundamental principles. The work that we're doing is basically going to provide the high-level intent and purpose of each of those generic principles, and then show a whole variety of different ways different people achieve them. And so in each of the 4 case studies that we've got under our belt right now, addresses these things different ways, but they have the same intent and the same purpose that they're trying to achieve. The product architecture has to be agile. We saw that in all cases in order to facilitate the abilities of the Agile System engineering process. The asynchronous simultaneous Agile lifecycle framework, that circle diagram was confirmed everywhere we looked. People were doing stage work in a variety of stages simultaneously and shifting asynchronously between them. The research life cycle stage, we saw it everywhere. We looked different ways. And what was useful is that what we saw at Lockheed in terms of flow measurement was very critical for them to be able to maintain what they had to do, whereas at Northrup Grumman, what was critical to them was to eliminate the surprises they were getting from the external environment. So we see this basically everywhere we've looked. The stage engagement criteria on that circle, we haven't done a lot of detailed life cycle model activity yet, and we may never do that, principally because from a generic concept, what we're interested in is the ability to move into those stages triggered by the awareness that it's time to do something because we have the necessary knowledge in order to start doing that right now. Methods observed, I covered some of those. I put that in there toward the bottom. Scrum-like software development, we saw that everywhere. I don't put SAFe up there because SAFe at heart is Scrum. It's scaled Scrum. And the Scrum is more fundamental in terms of saying that it works well in the software development environment. But fundamentally, what Scrum is all about is good project management activity. And the kinds of things that you see in the Agile Manifesto, for instance, are good project management activity. And the Agile Manifesto really doesn't tell you what enables agility. It tells you how to eliminate some of the barriers of what will impede agility. And it does it very well. But you can apply those in a lean environment or in any other kind of environment as well. Okay, next slide. Epilogue. I promised that there would be some talk about Agile hardware development, and you saw some of that, especially at Rockwell Collins. We didn't talk in detail about the kind of tooling that they've built to enable success of incremental development of firmware and circuit cards. And you can read about that in a case study, where there's a lot more time and a lot more words available. But the thing worth noting here is that too many people think that, oh, that Agile Manifesto works so well over here, all we need to do is slide it over and change a few words into the hardware environment. That doesn't happen. I'm sorry. In fact, that doesn't even help the agility of what's gone on. One of the things that's very key in the Agile software development processes is that they use an object-oriented development environment for their code development, C++, Java, Eclipse, things like that. Or if they're working in a web environment, they've got an inherently loosely coupled architecture for the pages and links that they've got. So they don't even think about the requirement of how important it is to have that platform there. Well, I'm sorry, the hardware people don't have such a platform. They have to build it, and they are building it. Product line engineering is proprietary for every application in it's in. Well, that's not totally true. I mean, there are some things out there that you can take a product line view of that deal with open systems environment community. So it's not especially proprietary, but it is still within a given domain of the kinds of things that you can have in that product line. Open system architecture is very much something that enables the agility of the product. But virtually every place it's used, you got to develop your own. There is no standard that can be applied in a large domain for open system architecture. That's not to say it won't come to pass, but it hasn't happened yet. One of the most interesting things to me is this thing called Live Virtual Constructor, LVC. Gets a lot of application in certain military applications, and basically it's an environment that, much like the Lockheed ANTI, where you've got an ability to connect up simulations, real devices, and people. That's the Live Virtual Constructor part. And they can all interact with each other, even though some of them are only simulations, they aren't done yet, or some of them are prototypes, they aren't finished devices. And so you get a very early ability to start asynchronously going through system development in a variety of multiple disciplines without having to have everybody lined up at the same time. There is not a good LVC application out there that's available from a common off-the-shelf point of view, but within the military with high-level architecture concepts, HLA, I mean, that is a standard on the high-level architecture concept for a live virtual constructive platform in a certain set of military environments. We start seeing a broadening of the domain of application for LVC. Here we are at 502. Okay, so here's some examples of infrastructure-enabled agile hardware system development. Some we've already seen in the top part. Rockwell Collins, the Navy, and Lockheed are things that are discussed in the case studies. There's an excellent paper that's done at L3 Communications that talked about aircraft infrastructure that basically took an architectural approach that made it a lot easier to put new stuff into an aircraft without having to replumb for ventilation, heat, and power. To my knowledge, the paper that was written on that, which was a term project for a student, did not get implemented fully, but some parts of it have been. Team WikiSpeed, some of you may have heard about. There's nothing written on Team WikiSpeed. It's all video, and some of it's really quite excellent. The guy builds cars with the hardware, and has found some very interesting ways to deal with the asynchronous development of multidiscipline activity. The book down at the bottom, Responsibility, one of its 4 principal examples is applied materials semiconductor fabrication machine design, highly agile concept. For those of you who are interested in those things, those are some references in that space. For those of you who are waiting for the hover car, like many of us have been for decades, 3D printing in metal parts seems to be that same thing. But all of a sudden, and this is only a few days old on the web, here's something that the Army took 4 different approaches to, some of which worked much better than the others, and to actually produce both the gun and the ammunition for a grenade launcher in a variety of different ways that was all 3D printed. And my message to those of you who are in a position to think about it is that 3D printing of metal parts may actually be ready for a good set of applications already and needs to be looked at. And that doesn't mean you need to go out and buy a bunch of 3D machines. That means you need to find a subcontractor who can build some of that stuff for you, who has the machines. And that takes us to the final slide. References, the ones in blue are those 4 case studies. They are available now for download.